So let's look at an application with a linear function. So we're looking at the life expectancy for males in the United States from the year 1910 until 2000. So we're modeling it with the linear function L of x, which is 0.27x plus 48.3. L is representing life expectancy, and x is the number of years since 1900. So the idea being, if we have, switch to, let's make that x instead of t. So where we have an x value of 10, if that's 10 years since 1900, then that would be the equivalent of 1910. A lot of problems will do this, especially with years, because it's much easier to work with these smaller numbers. So instead of having to plug in 1910 just to represent a time period, what we can do is have x represent this kind of amount of time that's passed instead. But what can be helpful with this, especially when you get into writing sentences, is to write these dates off to the side, just so you do know what matches up with what. So 1940, 1955, 1970, 1985, 2000. Okay, so filling in the table, what I'm going to do is use the function. So we have 0.27x plus 48.3, and I'm just going to plug in these different outputs. So with this is where I like Desmos a lot. Well, I like Desmos a lot for so many reasons, but another great reason is that we can do this 0.27 times and then 10 plus 48.3. And if you leave it like this, you can see, like I haven't hit enter yet. It'll show you the answer. So we have this answer of 51. And then what's nice is if you need to go plug in 25 now, if you go back, you can just edit it. So take out the 10, plug in 25. So it's just kind of fast for getting these numbers out by just replacing them. So go ahead and do that, plugging in these values, 59.1, 63.15, 67.2, 71.25, and 75.3. Alright, so let's look at interpreting some of these values. So find and interpret the vertical intercept of the function. Well, with that we can just look back at our function, which is in slope-intercept form. So we have an intercept of 48.3. And this is happening when x is 0. So how we will interpret this is that we have an input of 0, and in this case x is representing time. So it's like we're in year 0, which actually for us is the idea of the year 1900. And this output is representing the life expectancy of males in the United States. So what I could do is just make a little note to myself, life expectancy is 48.3 years. So I like to do this with these interpretation problems of just kind of working with the numbers, take this little middle step to just kind of jot down notes that can help me. And then once I see these notes, it's easier for me to put together that, okay, in 1900, the life expectancy was 48.3 years. So let's go ahead and write that down. So the life expectancy for males in the U.S. was 48.3 years old in 1900. All right. Find and interpret slope. So with slope, we have a slope of 0.27. With slope, I think of it as we increase our input by 1. So in this case, we're going to take x and increase by 1. In this case, that would be the idea of increasing by 1 year. So we're going to go 1 year beyond 1900. So for each year beyond 1900, this number is how the input changes. So slope is showing us for each single increase for x, the slope is our increase or decrease for the output. Now in terms of if it's going to be increase or decrease, that'll depend on the sign of the slope. This is a positive case, so we're seeing an increase. So what this is telling me is that life expectancy will increase by 0.27 years for each year after 1900. So this is where I might even kind of talk to myself for a little bit. It just takes time to get that sentence together. So, life expectancy is increasing 0.27 years for each year after 1900. Let's write something like that. The life expectancy for males in the U.S. increases by 0.27 years for each year after 1900. Alright. Find L of 50. So with that we can just refer back to our table. So next to, no we can't, 50 is not on there. So we're going to plug it in. So we're going to do 0.27 times 50 plus 48.3. And plugging that into the calculator, we should get a 61.8. Alright, so 50 is giving us the amount of the number of years after 1900. So this is giving us the year 1950. And then L, which is the output, this 61.8, this is the life expectancy. So we're getting the 61.8 years old. So in 1950, the life expectancy of U.S. males in the U.S. was 61.8 years old. Alright, L of x equals 60. Now we're going to plug into the other side of the equation. So we know our output is 60, and we want to find out what x is. So we're going to solve for x. So I'm going to go ahead and subtract 48.3 from both sides of the equation. So that'll give me 11.7 equals 0.27x. Then I'm going to divide both sides by 0.27, and that'll give a 43.33. And this right here, just keep in mind that x is representing years after 1900. So this is like the year about 1943, kind of a third of the way into 1943. So it's during that time, and then 60 is the life expectancy. So we could say in about 1943, the life expectancy of males in the U.S. was 60 years old. Alright, so there's an application using our function notation and with a linear function thinking about slope, intercept, and then how to interpret these inputs and outputs.